When I first started building websites and web applications 20 years ago, nobody talked about cybersecurity on the web. The truth is that the technology that underpins the web has changed considerably over the years, and the technologies that developers choose to build their applications and their websites has also changed quite a bit. The landscape of tools and technologies that developers can choose from today is wider and deeper than ever, and JavaScript libraries like React and Angular are among the most popular choices for developers today. React in particular has become popular because of its reputation for mitigating attacks like cross-site scripting. While React does do a good job of mitigating cross-site scripting attacks, it should be noted that it can't prevent every possible attack. Let's dive into some specific examples so that we can better protect our applications from the threats and attacks they will face in the real world. Welcome to HackingReact.io, another web application that we can use to demonstrate security concepts within modern web applications, specifically those built with React. As we just discussed, React does a really good job of mitigating most cross-site scripting attacks. In this first example, we have a basic HTML input box, which takes any user-supplied, unsanitized content and attempts to render that directly to the DOM. This is an interactive example where you can continue typing into the input box and see that content rendered directly into the web page below. By default, we are providing an HTML image tag with no source attribute, but an onError handler which is going to execute any JavaScript should the image fail to load. This is a classic cross-site scripting example because this onError handler is going to fire because there is no source attribute. React correctly handles this input, rendering it as a string to the web page instead of interpreting that HTML image tag literally as HTML. So if React is handling this for us automatically, and we didn't have to do anything extra, what's the problem with React? Example number 2 starts out by displaying an alert box, presumably because we were successful in executing a cross-site scripting attack. Clicking on the OK button will get to the content for this example. The problem with this example is that we've changed the way in which React renders the output. Rather than rendering the raw output in the default manner, we're using dangerously set inner HTML, an API built into React with the explicit purpose of allowing us to do dangerous things. If you focus your eyes at the bottom of the screen in the little gray square, we can see that React did attempt to render this image tag as literal HTML, and it did not try to sanitize our user input and display it as a string. The browser attempted to render the image tag, but with no source attribute. The browser attempted to execute our onError handler, which has a JavaScript alert box. Needless to say, you really shouldn't use dangerously set inner HTML unless you're really, really careful. How can we fix this problem? Thankfully, many JavaScript libraries exist to help us sanitize user input, specifically anything related to HTML. This example uses a library called DOM Purify, which we will use to clean that HTML and then pass it to dangerously set inner HTML to render as safe HTML output. Focusing your eyes at the bottom of the screen at that gray square once again, we can see that React attempted to render the HTML image tag, but it did not execute the raw JavaScript included in the onError handler. DOM Purify has sanitized that part of the input to make this HTML tag safe for the application to render. Unfortunately, React also has other scenarios where it doesn't protect unsanitized user-supplied input for us. Let's take a look at the next example. In this example, we are taking unsanitized user-supplied input to give to the HTML anchor tag's href attribute. This pattern is fairly common among web applications, specifically any web application that has a user profile, which may ask the user to provide a link to their homepage. Because developers can be lazy, they'll typically take the value provided by the user and shove it directly into the anchor tag's href attribute. The problem with this example is that the browser supports all kinds of protocols in link tags, not just HTTP or HTTPS. This example uses the JavaScript colon protocol. And if we scroll the page down slightly so we can click on the compromised link, what we'll see is that it in fact executes our malicious payload. This pattern is also fairly common with buttons that have some kind of on-click functionality, where we can click the button and again it's going to execute our malicious payload. So if React is not going to protect us from cross-site scripting attacks like this, how might we protect our applications by ourselves? Example number 4 highlights the use of some native functionality within JavaScript to help us sanitize things like links. When a user provides a link, we can wrap it in the new URL class to get a sanitized version of the URL, which we can then use to compare the protocol to make sure it's something that is supported by our application. We can even provide it a default value if the user has provided something malicious. In this example, now the anchor tag as well as the buttons on click are properly secured. One final comment on anchor tags and buttons is that React isn't alone in being susceptible to these kinds of attacks. Angular, Vue.js, and pretty much every other JavaScript library available is going to have problems with the JavaScript protocol. You should definitely be on the lookout for these in your own application. Let's move on to the next example. We should take a step back and talk a bit more about application architecture to better understand the threats that an application faces. There's effectively 5 ways that an attacker could use to inject a malicious cross-site scripting payload into the application. We've already talked about a few of these, both in Hacking React, as well as our previous example, the Cyber Scavenger Hunt. In the Cyber Scavenger Hunt, we talked about ways to inject malicious content using the URL parameters, local storage, and certainly anything that the user is going to input via the keyboard. Some additional areas to be concerned with would be any communications coming into the web application from outside sources, things like APIs and WebSockets, as well as any child windows or frames that might be opened by the parent application. It's important to always be on the lookout for user-supplied, unsanitized content, even content that's coming to us directly from a database that we trust. The key to protecting modern web applications is to deeply understand all of the ways an attacker can get a payload into the application and never, ever trusting that data, no matter where it comes from. But what happens if, despite our best efforts to prevent a cross-site scripting attack, a malicious user is still able to execute code within the browser? It's not realistic for every web application to protect itself against every possible attack vector. Hackers are really smart. Something we should do is better understand what an end-to-end cross-site scripting attack looks like in real life so that we can put ourselves in the best position to prevent those attacks from executing successfully. Let's make up an example. If a cross-site scripting attack executes an alert box in your browser, that really doesn't do a whole lot of good for the attacker. They can't use any of that information because it's on your machine. The attacker needs to get data from your machine to their own machine in order to make use of the data. And the way they're going to do that is using a command and control server. A command and control server allows an attacker to listen for communications from a successful cross-site scripting attack on any other browser. You can imagine code executing in your browser, maybe looking for a session cookie or a JWT in local storage, or a user ID or an input of any kind. An attacker is going to try to execute code that can communicate those values back to their command and control server so that they can use that information without directly accessing your machine. The moral of the story is that if we can prevent the outbound communication, then an attacker will never be able to find the values they need to complete the attack. To prevent that outbound communication, every web application should implement a content security policy. A content security policy is simple to implement. You can either add it to an HTTP response header or the HTML file hosting the application. In either case, you can explicitly whitelist certain domains and third parties that the application is allowed to communicate with. Any domain that's not included in this policy will be blocked from sending outbound communication. Going back to our example of the command and control server, you can understand how even if code executes in your browser thanks to a cross-site scripting attack, the outbound communication will be blocked and the attacker can never use that data. It's almost like the cross-site scripting attack never happened. At this point in the course, we've talked about a lot of security concepts through the lens of a web application developer. We understand the libraries, the tools, the browser extensions that a developer might use to build their application, and we certainly understand how an attacker is going to use all of those same concepts and tools to enumerate the data in your application. In the next part of the course, we're going to flip that lens and look at security through the eyes of an attacker. We're going to dive into some examples on Hack the Box and use Parrot OS to break our way into some vulnerable web applications, and we'll talk about strategies that we could use to protect our own applications. Are you excited yet? This guy sure is. Let's jump into the next lesson and start hacking some apps.